Greetings, everyone. I'm Captain Pankaj Pahil. With 17 years of experience training pilots across the globe, I'm here to guide you through the intricacies of the DGCA syllabus. Welcome to today's ground school session. Look, if you're preparing for your CPL or ATPL air regulations exam, you are in exactly the right place. Today, we're unpacking special operational procedures and hazards. So, let's look at the boards and dive right into the technicalities. I want to kick things off with a thought I always share with my students. Aviation in itself is not inherently dangerous, but to an even greater degree than the sea, it is terribly unforgiving of any carelessness, incapacity, or neglect. I really want you to internalize this. The regulations we're about to study, they aren't just hurdles for your DGCA exams. They are literally written in blood. They demand rigorous discipline. Keep that mindset front and center as we proceed today. All right, today's agenda covers 6 key phases. 1. Pre-flight. 2. Ground ops. 3. Takeoff and departure. 4. In-flight emergencies. 5. Wind shear and wake turbulence. And finally, 6. Landing hazards. Let's get moving. Starting with Section 1, Pre-flight. We're focusing on the MEL and AFM chain of authority here. Now, you might be wondering, where do our operational rules actually come from? Well, the chain of authority begins with the manufacturer. They draft the Master Minimum Equipment List, or MMEL. But here's the thing, you don't fly the MMEL. The operator takes that master list and tailors it to create its own MEL, specific to its actual fleet and routes. But the absolutely crucial point here is that the DGCA must approve both of these documents. No approval, no flying. So here's a massive exam tip for you. The MEL is exactly what the pilot in command uses to make that final go or no-go decision when a piece of equipment fails on the ramp. And note this limitation carefully. The operator's MEL can never, under any circumstances, be less restrictive than the manufacturer's MMEL. I mean, if the manufacturer says you need 2 operating generators, the operator cannot just decide you only need 1. It doesn't work that way. Beyond the MEL, we have the Aeroplane Flight Manual, the AFM. These represent your critical safety limitations. The AFM contains the certified performance data established by the state of design. An aircraft must be operated strictly within these AFM limitations. Guys, these are absolute legal boundaries. They are not friendly suggestions. Moving on to Section 2, Ground Operations, specifically de-icing and contamination rules. Let's break down the rules for contamination. We've got 2 distinct procedures here. De-icing removes existing frost or ice, while anti-icing protects the surface from future accumulation. Standard operating procedure mandates an inspection before takeoff if you even suspect icing conditions. Now, listen to this critical limitation. Aviation has a zero-tolerance policy for ground ice. Even 0.40 millimeters of roughness, which is practically nothing, severely disrupts your lift. And for your exams, be incredibly wary of a phenomenon called cold soaking. When you cruise at high altitude, you deeply chill the wing structure. Then, when you land in a humid environment, moisture freezes instantly on contact, creating this invisible, clear ice. You can't just look for it. It often requires a physical, tactile inspection to detect. All right, Section 3, Takeoff and Departure and Noise Abatement. Now, noise abatement procedures are designed to keep our neighbors on the ground happy. However, you absolutely must memorize these strict limitations. Never execute a noise abatement procedure below 240 meters or 800 feet above aerodrome elevation. Also, never use them if wind shear or downbursts are suspected. Standard operating procedure is crystal clear. Safety always supersedes noise abatement. For your DGCA exams, remember the 15-5 dry rule. If your crosswind component exceeds 15 knots, your tailwind exceeds 5 knots, or if the runway is not clear and dry, noise abatement cannot be the determining factor in your runway designation. Section 4, In-flight emergencies. We're looking at fire and decompression. The classic fire triangle requires 3 specific elements for combustion: oxygen, heat, and fuel. Together, they create a chemical chain reaction. The core goal of all firefighting, whether you're on the ground or cruising at 35,000 feet, is simply to eliminate at least one of these elements to break that chain and extinguish the fire. It's that simple, but the execution is everything. How we actually eliminate that element totally depends on the class of fire. Class A fires, like paper or fabric, are fought with water. Class B fires involve flammable liquids like aviation fuel. Class C is electrical. Class D involves flammable metals like magnesium. You have to pay strict attention to the limitations here. Never, ever use water on a Class B fuel fire. You're just going to spread it everywhere. And never use halon on a Class D metal fire because it can trigger a highly dangerous chemical reaction. Our other critical high-altitude threat is cabin decompression. Let's talk about explosive decompression. It happens in less than half a second, instantly filling the cabin with fog, dust, and flying debris. The moment this occurs, you are fighting your own time of useful consciousness. The absolute immediate response is to dom your oxygen masks. You can't fly the plane if you're passed out, right? Once your mask is on, initiate an emergency descent immediately to an altitude where supplementary oxygen isn't required, which conventionally is 10,000 feet. Moving into Section 5, wind shear, wake turbulence, and dynamic hazards. Think about the sequence of a microburst encounter. First, as you approach it, you hit a really strong headwind. Because of this, your performance temporarily increases, and the aircraft actually tends to pitch up and rise above the glide path. Then suddenly you fly straight into a massive downdraft. Finally, as you try to exit, that strong headwind instantly turns into a massive tailwind. This completely robs the aircraft of its lift, pushing you into a critical sink rate precisely when you are closest to the ground. It's a highly lethal trap. You must memorize these DGCA exam tips regarding microburst characteristics. They're actually quite small, typically about 1 nautical mile in diameter at 2,000 feet, but they are incredibly violent. You can expect vertical downdrafts as severe as 6,000 feet per minute. To put that in perspective, that's plunging down at over 60 miles an hour. Furthermore, they are short-lived. The entire life cycle of a microburst, from the initial downburst to total dissipation, is seldom longer than 15 minutes. Another invisible threat we face is wake turbulence. Basically, these are horizontal tornadoes trailing behind a wing producing lift. Strict separation minimizes this risk. Look out for this specific exam trap. If you're flying a light aircraft arriving behind a heavy A380, you require exactly 4 minutes of longitudinal separation. Don't guess this number on the exam, just know it. These vortices sink and spread out over time, and that separation time is literally the only thing allowing them to clear your flight path. Finally, Section 6, landing hazards, runways, and brakes. Think of dynamic hydroplaning like driving on black ice with bald tires. When a runway has standing water that's deeper than the tread depth of your tires, and you touch down at a high speed, your tires can literally lift off the concrete. They end up riding on a thin cushion of water, exactly like water skis. When this happens, directional control and braking action become virtually impossible. You are no longer flying an airplane, you're just a passenger to momentum. So, to combat the massive risk of wet runways, the DGCA mandates a strict buffer. I want you to burn this exact figure into your memory right now. If weather reports indicate the runway may be wet at your estimated time of arrival, the required landing distance on a dry runway must be increased by 15%. That is a 115% multiplier. Don't forget it. And of course, sometimes we never even leave the ground. A rejected takeoff, or RTO, at high speed means we are forcing the aircraft's massive kinetic energy to dissipate almost entirely through the brakes. Heavy braking creates incredible friction, which translates into massive heat generation. This extreme heat can lead to rapid tire deflation, total loss of directional control, and incredibly dangerous thermal bursts. Which brings us to a crucial, life-saving safety limitation. After high-speed RTO, when fire guards or rescue personnel approach the undercarriage, they must always approach sideways, meaning from the front or the rear of the tire. Never face the sidewall. You have to avoid lethal shrapnel if a thermal burst happens. And a huge warning for the flight crew. Never apply the parking brake with overheated brakes. The extreme heat will literally fuse the assemblies together permanently. To wrap up today's session, let's synthesize all of this into our ultimate takeaway. From dispatch legality with the MEL to facing ground ice, violent microbursts, or contaminated runways, the commander holds ultimate responsibility. Across all DGCA regulatory scenarios, remember this simple truth. The correct answer always prioritizes proactive avoidance over reactive recovery. Do not test the margins, master the rules. Because the next time you face a severe downdraft or a flooded runway, it won't be a multiple choice question. It'll be real life. So I'll leave you with this. Are you ready to make the right call?